Good morning. Today we'll discuss about magnetic potentials. In the last class, we have discussed about Ampere's law and also the applications of Ampere's law in determining magnetic field intensity and also flux density. In today's class, we'll discuss about magnetic potentials. They are just like your electric potentials, but a slight difference is there. So I hope that by the end of this lecture, you'll be able to give me a brief introduction about magnetic potentials. Coming to the introduction, we have seen in electric fields that an electric flux density, and also we have seen a term called as V, which is referred to as electric potential or electrostatic potential. Right? It used to have units of volts. The units were volts, and it used to be a scalar quantity. So, but whereas in magnetic fields, we do have two different types of potentials. One we call it as a scalar magnetic potential, which is a scalar quantity, and the other one is vector magnetic potential, which means that we should compute two magnetic potentials, but in two different cases. At any point of time, only one will exist. So sometimes we need to calculate scalar magnetic potential, and sometimes we need to calculate vector magnetic potential. So that we will calculate today. Okay. Normally, electric potential is represented as V. Scalar magnetic potential is represented as U, and it is a scalar, whereas vector magnetic potential is represented as capital A, and it is a vector. Now, we'll start with a small introduction to scalar magnetic potential. It is often represented by the symbol U, and it is a scalar quantity, and it is defined only in regions where J is equal to 0. We have already discussed about J. J is the current density, and J is a vector, and its units are ampere per meter square. So, scalar magnetic potential is defined only in the regions where J is equal to 0. As we have seen in electric fields that E is equal to minus del D, right? This was what we have seen in electric fields, right? Similarly, this is electric field intensity, this is electric potential, right? Similarly, just like that, we define in magnetic fields that magnetic field intensity is H, right? And this is what we have written here. This is scalar magnetic potential. Just like here, scalar electric potential, this is now scalar magnetic potential. But do remember, it is defined only in the regions where J is equal to 0. Okay. Yeah, it is similar to that of electric potential, which is, this is V. Just like this, how it happens in electric field, the same will be there in magnetic field also. And in particular, this satisfies Laplace equations. You know that Laplace equation. What is Laplace equation, right? Del square some quantity, so P is equal to 0, right? So here U satisfies, U means scalar magnetic potential, it satisfies Laplace equation, which means del square U is equal to 0, and the condition is current density must be 0. So this is with regard to scalar magnetic potential. And coming to vector magnetic potential, this is the second term which we will be going through in this magnetic potential concept. This is often represented by a vector symbol A, and it is related to magnetic flux density as follows. This is the equation. Okay, B is equal to curl of A. Try to remember this one. B is equal to curl of A. And let us suppose if you do have current elements, we know that we do have different types of current elements. This is a line current, this is surface current, and this is volume current. So when you do have these type of elements, Then how to compute magnetic potential? These are the equations. A is equal to mu I dl by 4 pi r. Okay, try to remember these equations. And in particular, if you carefully see, these are for, this is for line current, and this is for surface current, and this is for volume current. Okay, and let us suppose how to determine magnetic flux. Determining magnetic flux when magnetic vector potential is being given for you. Normally, magnetic flux is represented by the symbol phi, and it will be having Webers, right? So how it is determined? It is determined, right? This is a normal expression which we use for determining magnetic flux from magnetic flux density. In other words, we can use this one also. Okay, so if A is given for you, how to determine the magnetic flux? This is the equation. Okay, and one more thing, few more things to remember in this magnetic potentials is, you know that this basic expression B is equal to mu h. It is very similar to your electric fields, right? And we have already seen in the previous classes that del cross H is equal to J, right? Which means if I apply mu here on both sides, what will happen? This is mu H, this is mu J, right? You know, this is B, right? So del cross B is equal to mu J. This is the expression. And the last one we have seen that B is already equal to del cross A. Right? If I substitute this one here, what you will get? Del cross A is equal to mu J. Right? Try to remember this one. Del cross A is equal to mu J. And regarding the divergence, do remember del dot H is equal to 0, whereas del cross H is J. Del dot J is equal to 0. Try to remember this one also. This will be helpful for us when we do the problems. Okay. Now, that's it for today. I hope that you are now able to understand and use small information regarding scalar and vector magnetic potentials. If you do want more details, you can go through the textbooks, Matthew Sadiku and K. Gangadhar. You can find some interesting concepts on scalar and magnetic potentials in those textbooks. Okay. So in the examination, I will ask this one more question on this magnetic potentials. Write short notes on scalar and vector magnetic potentials. Try to answer them. That's it for today. Thank you.